Mathworks to please come on.
The gap between algorithm development to porting it onto the hardware and making it work on the hardware. So I would like to talk about MATLAB and Simulink, why I advise you to use them, because it's mostly a model-based design which helps you in evaluation of your algorithms at much easier way, and also adapt to any specification changes faster, and also to evaluate your design alternatives, your multiple algorithms before you implement them and put it onto the hardware. So this is the general workflow that we follow. So the first one is to design your, fix on an algorithm that is your application specific. Then you generate HDL or the C code for the design that you have decided, and then use HDL verifier to verify the generated HDL code, whether it could be Verilog or VHDL, and then deploy it onto FPGA or SoC, whatever your board requirement is. And if you face any issues on the FPGA, I would talk about features that you can use to debug on the FPGA. So first coming to the design. So in the era where we need high bandwidths and higher throughputs, our design should be very much in line with what is our requirement. So if you're working for an application where you're targeting higher bandwidths or higher throughputs, or you want your application to work at lower SNRs, we have to decide on what exactly is our requirement and what is our target. So I will take a case where we want higher throughputs. So one way that we can achieve higher throughputs on FPGAs, because in general FPGAs have their own limitations to support higher throughputs, whether it could be their clock rate or their resource utilization. So one way to achieve higher throughputs is to go from sample based processing to frame based processing. So if you see here the two chains, the above chain runs for frame size 1, whereas the below chain runs for frame size 4. There is no difference in the chain that you see here. The only thing that you guys have to do is to feed in instead of scalar a vector size, so that the chain runs as it is. So that's what we do. We develop blocks which work both for sample based and frame size, eliminating the work that you have to do around it. So the same chain that you develop for scalar based can still work for the vector based. So what happens when we do this? Although there is slight increase in the resources because we are processing 4 samples at once rather than 1 sample, but the throughput that you can achieve here, if you see with frame size of 1, you are only able to achieve 400 MSPS. But if you go to, since you're processing 4 samples at once, you can achieve 1.6 gigasamples per second. So this is one technique where you can achieve higher throughputs on FPGAs. So these are the blocks that are there in our DSP HDL toolboxes, which work both for sample based and frame based. So you don't have to write anything from scratch. You can pick the block from the toolbox and start off from there. Now coming to the applications that we have applications for 5G, LTE, WLAN, custom applications, and right now we have SATCOM, satellite communications. So all the codes or all the blocks that are there in this can be ported onto any hardware. They are not hardware compliant. You can choose any board of your requirement and you can port the code. So whatever we generate whatever we develop will work with any ASIC board, FPGA board. So these are the blocks that we have in wireless HDL toolbox. We have standard specific blocks, demodulators, decoders, modulators. So if you are building some chain, you can pick blocks from here, connect them and still work. So now we are talking about design and implementation workflow. So the 3 things, the traditional way what we do is we first write the floating point or our algorithm in MATLAB, evaluate them. So what we call as golden reference algorithm here. So here I am taking a 5G example where I am writing an algorithm using MATLAB functions from 5G toolbox, and then so whatever algorithm we write may not be feasible on hardware, because when we go to hardware we have to write our algorithm in such a way that it has time constraint in it, since we access only 1 sample at a time. So here I have an example in 5G as I've mentioned, which does SIB recovery. So we have 3 modules here which does SSB detection, SSB decoding, and then we are demodulating the SIB1 information. So this is the MATLAB algorithm. MATLAB is actually easy for you to, a great way to explore your algorithms. So here we have 3 functions that we are doing, and that is our first step. So we have an algorithm ready, and what we do is we implement a fixed point implementation, because in hardware we want everything to run in fixed point and not floating point. The same thing that we have, this is the Simulink. This is the Simulink environment that you see. Instead of MATLAB functions, you have blocks as I've just shown in the toolboxes. So we have 3 subsystems here which do a very similar thing that we have written in MATLAB. So one does SSB detection, then we have SSB decoding, And then we have resource grid optimization, demodulation. So this is something you can simulate and verify your code, whether are you able to achieve the accuracy or whether the performance is as expected, things like that in Simulink. This helps you in rearranging your architecture also so that it achieves best results on the FPGA. And whatever subsystems you see, each one is verified individually. So we don't build the complete system and then verify, right? When you write a piece of code, you verify it individually and then integrate into a larger system. So for example, if I consider SSB decoding subsystem here, this is how the unit testing that looks like. So we only have that subsystem. We push the inputs that we know and we know what kind of outputs to expect, and that's how verification happens. Okay, now we have our algorithm ready, which is in fixed point, which is in Simulink. Now we have to generate HDL code for it. So we have HDL coder inbuilt in MATLAB, which generates HDL code for any modeling languages. Okay, this is before LLM comes handy for us. We can use this workflow, which generates HDL code for any application domain, any complex maths you have in your algorithm. And you can feed any MATLAB functions. If you have only MATLAB function and no Simulink models, you can feed Simulink models. You can actually feed DL networks as well, and your HDL coder will generate the HDL code for you. And one more added benefit of using HDL coder is whatever HDL code it generates, that is optimized in terms of speed, in terms of area, I mean the resource utilization on the FPGA, the IO. And one more thing that you can do is, even if you don't have a particular board, say you want your algorithm to work on Zinc 706 or any FPGA, you can choose that board and run synthesis and implementation. You don't have to open Vivado tool to do all this. So it's all automated in the through HDL coder. So you can look at the synthesis results or the implementation, what frequency you are able to achieve or what kind of resources it is consuming. And if you want to improve your design, you can go back to your Simulink model or your MATLAB code, change and do the same thing again. So you're not shuffling between the apps, loading, unloading the projects. You don't have to do all that. It's all automated. Now I have my HDL code. I have generated my HDL code. And now what do I do? So from Simulink model, I generated HDL code, and how do I be sure that my HDL code is working fine? So you can use HDL verifier, which does two things. You can use two things to verify your algorithm or the generated HDL code. Is do HDL co-simulation or FPGA in the loop. Let me talk about HDL co-simulation. So this basically enables you, assume you are given only one task of developing a certain block and the rest of the chain is already there. So if you want to verify only that portion, you can use HDL co-simulation, which generates HDL code for that particular block and runs in the same chain as the Simulink. So in this, if you don't, or suppose you are not writing anything in Simulink and you have handwritten RTL code, you can still put your RTL code in this chain and run the system. So this helps in not porting completely onto the FPGA and run things. You can still do it in simulation level and fix any bugs that you may face. So this way it helps in reducing the time taken, because you can use the same test bench again and again to verify your simulation. And it also makes you help understand whether your RTL design is compliant with your algorithm specification or not. So this also helps in verifying the accuracy at bit level, and it saves time, as I've mentioned. Using the same existing test bench, you can run multiple simulations and fix the bugs. There is a use case where Meteorcom has used the same HDL co-simulation for verification of their digital down converter, and this helped them reduce the development time from 9 weeks to 3 weeks, because they were able to do it in the same environment and not save, upload, generate multiple test benches again and again. And the next one is the FPGA in the loop. So in HDL co-simulation, what happens is everything runs in software. So it runs in HDL simulator, the Verilog code. So if you have an applications that you have to test for large sets of data, running in simulation could consume a lot of time. So what FPGA in the loop does is, you have your proof of concept, which you can deploy it onto FPGA. You push inputs from MATLAB, take outputs into the MATLAB and do verification. So this is all automated. You don't have to do the bitstream generation, everything. So if you use this FPGA in the loop app, it automatically generates bitstream and the software interface, whatever is required to run. And this helps in running the code much faster. So we have Intel, which use the same FPGA in the loop concept for their, they had to do it for LTE turbo decoder. And if they had to do that for large sets of data, it would ideally consume 21.5 days, which is close to impossible. And using this FPGA in the loop, they were able to reduce it to 23 minutes. You can see how fast you can run it on hardware, and that is what we are caching here. Now you have verified your HDL code, whatever you have generated, you fix the bugs, whatever you have seen, and you have working RTL code. And how do you deploy it onto hardware? Before you deploy your system onto hardware, we need to decide what goes onto hardware, what goes onto software, and what should be the connections between the hardware software code. Like, you don't want to, maybe sometimes you don't want to put all the code onto hardware, you want to put some on this processor as well. So you have to decide all this. So for this interface model, so this interface model is critical for us because it will decide the layout on your FPGA. Now I have the interface model, and now is the deployment. You can use SOC Builder, the app here, which will help in automating. Once you feed in the interface model, it will take care of the bitstream generation, all the connections that we have given, and ports onto the hardware that is connected to your system. So ideally, we are only using MATLAB and Simulink to write your algorithm and port it onto the hardware. So although you don't have any knowledge of how to write a Verilog code or VHDL code, you can still do things on hardware, and this actually bridges the gap between the algorithm development and the actual deployment onto hardware. Now we have deployed onto the hardware. It is working as expected. Something changes over time, and how do you want to debug onto the hardware on FPGA? So in the same HDL verifier, we have two techniques or two features that you can use to debug on FPGA. One is the ECE Manager and the data capture. In ECE Manager, what happens is you can access the info DDR, you can configure the internal registers, you can send your own test vectors and get outputs. That's how you can see whether the expected design is working or not. And the FPGA data capture is something interesting where you can choose your test vectors. Suppose you feel the SSB is not getting detected, so you can actually choose the signals there, and you can name them as test pointers, and on the FPGA you can collect those signals directly into the MATLAB and and verify them. So this is one way which makes it a lot easier for you to use the known environment to debug things on hardware. Right now we have support to all latest boards from AMD Zinc Versal to Arria 10 from Intel, and also Zinc Ultrascale RF SoC and all the RF front ends. And there is lot of documentation that is available. Even though you don't know MATLAB much or Simulink much, there are on-ramp modules that you can use and get familiar with the environment, and also lot of documentation available on how to use HDL coder or verifier. This actually makes it a lot easier for you to, you can start off with a simple code as counter and try to see how it works. So that's all I have. I kept it short in the interest of time.
Without having any Vivado?
No, you need Vivado, but you don't have to open the app for you. You need the license for Vivado to run synthesis and implementation.
Okay.
Yeah.
The other thing is, without purchasing the whole bundle, is it possible to buy from MathWorks only that required HDL coder thing?
You can buy HDL coder alone, the license for that toolbox. Yeah.
So to whom? How to contact them?
I'll come to you. I can take the details and I'll ask someone from my office too.
If you are looking for internship in MathWorks,
okay,
how we can approach you people and what are the skills required for that?
Okay. Actually, we accept internships through professor
Actually, we're a bit
recommendations.
interested in MATLAB.
Sorry?
We have interest in MathWorks.
MATLAB.
Yes.
Okay. Ideally, we take internships through professor recommendations, but I can talk to you in person and I'll see what we can do about it.
Thank you very much for your insights, and thank you